Hi, I'm Art Neergaard of Guard Engineering and ShootingSight. Welcome to my program I call Engineer Guard, where exactly we do not discuss opinions or impressions, but I invite you in to open a can of science and go full nerd so that we can discuss physics and design principles of engineering to understand how things work and why. So come on in, let's get started. So let's get started. Today, I'd like to talk about RPS, rolled plate steel, and why it is a superior grade of steel to use in trigger design than cast steel. To begin with, let's talk about why cast steel is good. Cast steel is good because it's inexpensive. CNC machining is a very expensive operation, and so if you start with flat steel and need to machine the whole thing, it costs a lot. By casting, you can get 95% of your final shape done effectively for free in the mold, and you only have to machine the few little edges where dimensions are critical. In CNC machining, you need to machine the whole thing, so that's more expensive. Now, let's talk about what's wrong with casting. The problem with cast steel is that, assuming that we're talking apples to apples, we're talking the same grade of steel, we're talking similar heat treat processes, cast steel can have various defects in it. So to begin with, there are casting defects. When the liquid steel is poured into the mold, it can be turbulent, it can entrain small bubbles, which end up creating inclusions or voids inside of your finished part. The problem with those voids is they act as stress concentrators, and so cracks can start and propagate from these micro bubbles and cause catastrophic failure as your part breaks. Similarly, you can get what are called inclusions, where various alloying agents like carbon aren't fully dispersed and mixed up in the molten steel, and you get clumps of carbon that remain in the casting. Again, a clump of carbon in your finished part is an area where you're going to get a stress concentration, and you can get a crack propagating from there. There are testing techniques, magnaflux typically, that are used with cast parts to try and identify if there are inclusions or voids or stringers in the part prior to getting out to the consumer, but they don't always work. So you will find examples of parts that have failed in use. The other problem is that cast steel is about 10 to 20% weaker than rolled plate steel, and this is simply because of the nature of the grain structure in cast steel. When steel transitions from liquid state to solid state, it forms crystals, and the size of the crystals is a function of how quickly the steel is cooled. If the steel is cooled very quickly, it wants to form crystals badly, and so you get many small crystals. If the steel is cooled slowly, it forms fewer but larger crystals. You've seen this when you go outside in the middle of winter and it's 31 degrees, just barely below freezing, and it starts to snow. The water vapor tends to form large fluffy snowflakes because the temperature is not great for formation of crystals, but it's pretty good for growth of crystals, and so you get fewer large crystals. Conversely, if you go out on a day when it's, say, 5 degrees out, crystals form really, really quickly, and so you get very small, sharp, hard crystals. You see the results in snowbanks. A big fluffy snowbank is a lot softer than a snowbank made up of hard, sharp crystals. Same thing is true in steel. When liquid steel goes into a mold, the steel near the mold walls will cool more quickly. It will form small crystals. The steel in the middle of the part, where the steel cools more slowly, will form large crystals. It doesn't perform as well. What is the benefit to rolled plate steel is that you start with an ingot and then you run it through various rollers, each sequentially smaller and smaller, so that the ingot is squashed down and it flows and it effectively gets kneaded. This is similar to taking Play-Doh, where if you mix blue Play-Doh and yellow Play-Doh, at first when you put them together, you're going to see streaks of blue and streaks of yellow. As you start kneading in your hands, the streaks get smaller and smaller, and eventually you'll end up with green Play-Doh. Same thing is true with the steel. Large crystals get broken down, so you get a reduction of average crystal size. The crystals get mixed together, so the crystal size through the part is a lot more homogeneous. Similarly, if you get casting defects like microbubbles, inclusions, or stringers, these will get worked out and distributed through the part or eliminated through the kneading process of rolling. And so you get, as I said, 10 to 20% more strength in rolled plate steel. you get more homogeneous, you get reduced risk of casting defects. So the next question is now, why is this important for trigger designs? What I've done here is sketched up a really basic hammer and trigger. So you've got a hammer here with a hammer sear, a trigger with a trigger sear, and those two overlap with some area which is what's holding the hammer back. Now you've got a hammer spring on the hammer that's driving the hammer forward with a force of, say, 5 pounds measured at that distance from the pivot point. So we know force is 5 pounds. If we assume that our overlap there, just to make the math easy, let's say it's 1 square inch. So we know that our area is 1 square inch. From physics, we know that what really counts in the loading of steel is pressure. And pressure is force divided by area. So force over area is pressure, which in this case is 5 pounds per 1 square inch. So we've got 5 psi. Now, that's obviously a very low loading for the steel. It wouldn't bother anything. But what happens when you start to pull this trigger? This overlap here starts to decrease. So when you go from, say, 1 square inch of contact surface in your sear to 1/10 of a square inch, suddenly we've got the same 5 pounds, but now it's divided over 0.1 square inches. And so now we've got a loading of 50 psi. Take it a step further, when there's only 1/100th of an inch of overlap, we're up at 500 psi. Once you get down to 1/1000th of a square inch of overlap, you're at 5,000 psi, and from there you go up 10,000, 20,000 psi. As you get to zero engagement, in other words, the moment where the hammer gets released, at zero, you've got a force divided by zero area, which is an infinite pressure. Now, no steel can stand up to an infinite pressure, but what will happen is that at some point, the very tips of the sears will break down and round. And this is why the higher grade of steel you use, the higher pressure they can maintain before they round out, and so the sharper the sear edges will stay. If you get a low grade of steel or a very high level of loading, the edges will round out more quickly. With a high grade of steel, the edges will stay sharper. So this is why RPS triggers will always use rolled plate steel. We never want to use cast steel because that would be taking a step down and allowing the sears to have less of a performance life. They wouldn't stay as sharp for as long. So I hope that explains clearly why rolled plate steel is superior to cast steel when making triggers and hammers. Thank you for watching.